Oh,
Cara, que felicidade. Não, o pagamento não. Escreveu no chão do aeroporto. Eles cancelaram, eles adiaram o voo às 3 da manhã, falando que ia sair às 9. Daí não tinha nada de ir pro hotel, porque o hotel ficava 50 quilômetros, era o que eles pagavam. 50 quilômetros no cacete, não ganhava do outro lado, tem uma galera no vídeo. Certo? Não, é assim, zoado. Depois eu posso lembrar.
okay.
So that everybody down.
Okay, so good morning, everyone. Welcome to the second week of the program. I hope you had a good weekend. Yeah, enjoyed some fall a little bit. Even though the weather was not very cooperative, so some people went to Rio. You survived, I guess. Good. Barely. Okay, tell us later what happened. Or, you know, what happens in Rio stays in Rio.
You go to Rio with them and they stay in Rio.
So, so the second week is more focused on gravitational waves. First, and we have newcomers. So, Nick and Gabriela, thanks for coming for the second week. Yes. So we have a small change in the program today. So Riccardo is going to give an overview of gravitational wave astronomy. We're having a small break, and then Raul kind of giving the talk in the afternoon. We'll give the talk in the morning, and the afternoon will be mostly discussions for gravitational waves. I just want to remind you that last week we decided to have discussions of that the very discussion section. So we're going to talk about the discussion. So last week we put on the board a topics people would be interested in. Of course, CFT and simulation. So you and Matteo were going to coordinate the discussions on EFT of LSS, of bias and simulation and everything.
As dimension of square root of time or inverse square root of hertz in units that are commonly used. Why? Because you cannot give just the level of noise of your detector by giving a Fourier transform, no? Because that would depend on the chunk you use to take Fourier transform. If you take 1 hour or if you take 2 hours, the amplitude of the noise would change by the square root of 2. No? You change with the square root of the chunk of the detector.
So can you say it was N tilde?
Yeah, just the Fourier transform of the noise. And is
tilde is a Fourier, so
yeah.
N tilde has dimensions?
Yes, as dimension of time, because the output of the detector you take is dimensionless because it is proportional to the gravitational wave amplitude, which is dimensionless. So it's a time series which has discrete time steps. Then you take the Fourier transform, discrete Fourier transform, then you get something which has dimension of time, that it should be. And then you take the spectral noise density. So this is dimension of time, this is dimension of time, this is dimension of time, this is dimension of time. But this is quadratic in the noise. And that's the right figure of merit of your experiment. Okay, because you don't want the level of the noise to be dependent on how long the Fourier transform you took. Okay, so this object here, so this is in discrete. When you go in discrete space, this is one of the delta F, and one of the delta F is actually the thing which is proportional to the length of your chunk, and the spectral noise density is the right object which gives you the figure of merit of your detector, which is independent of how long the chunk you use. So that's why in all graphs that you see in papers about gravitational wave, you see either this function, which is quadratic in the noise, of its square root. And so this function is dimension of time or square root of time, depending if you want the figure of merit, linear in noise or quadratic in noise. Okay, so whenever you want to compare with noise in gravitational wave detector, you have to compare with these funny units. And that's the physical tick. So if you want to have yes, basically, if you want to have just a rule of thumb of what is the spectral noise density, you just take the Fourier transform of your chunk of data, but then you multiply by the delta F, because otherwise this object would be dependent of the length you arbitrarily chose to monitor the output of your detector. But this combination is independent of the length of the chunk. Okay, this is a bit technical, but just, you know, if you happen to read, I mean, one of the papers and you see these funny units, that's the reason why. So, and then I was pointed out earlier, so you get the best frequency of the bucket that is set by the optical path of the photons, and then you get these two main sources of noise, so seismic noise, low frequency, short noise, and then you have also thermal vibrations of, you know, the threads hanging in the mirrors, thermal vibration on the surface of the mirror, and then they are mostly responsible here at moderate frequencies. But I mean, those, of course, I mean, those you can tame by some smart engineer device. The seismic wall, I mean, is there. I mean, you can reduce it, but you cannot kill it completely.
So Riccardo, those spikes, what are they? I missed them.
And then there are spikes for all sorts of noise. I mean, this is just schematic. So there is a spike at 60 hertz that you might guess is the power line in the US, and it's 50 hertz in Virgo. And then there are all sorts of spikes here because the threads that are hanging in the mirrors, they must, I mean, you can make them as perfect as you want, but they must have a resonant frequency. So if you're unlucky to get something exactly the resonant frequency of the thread, then you get huge response. A good pendulum is not one that kills the peak of the spike, but it makes it very narrow. Because at the end, when you do the analysis in Fourier transform, it's very easy not to go to Fourier transform, chunk a very narrow frequency band and go back in time, and that's enough. So it doesn't matter if you have a huge spike at a very narrow frequency, because you can cut it out very easily. And that's what happens in the data. If you look at the data in time domain, you will see huge oscillations, few order of magnitude bigger than the amplitude of the wave, but those are at very narrow frequency band you don't care about. So you filter them out and you look at the ripple at the frequency you're looking at.
But for the events that have been detected up to now, which is the band? Is it close to the red?
Yeah, I mean, I will show you later, but basically what happens in this scale if you go from 10 hertz basically to the kilohertz, which is the standard bandwidth of terrestrial gravitational wave. So basically what you get is that the amplitude of the gravitational wave causes this typical frequency behavior, minus 7/6. This is analytical. The student who took my course know how to derive this. And then at some point, the signal ends at a frequency that is basically set by the inverse of the mass. Here, I mean, you're all gravity people, so you have no problem to accept that the frequency is the inverse of the mass. Particle physicists people have a problem with that, but not you. Okay, so basically the end of the signal is set by the mass. The inverse of the mass is the frequency. And basically the rule of thumb is that for 3 solar masses, this would correspond to a few kilohertz times m divided by 3 solar masses, the -1, and then you rescale linearly. So the end of the signal depends on the total mass of the system, and then you have this low -7c. Okay, this allows me to anticipate one features. You know, the signal, qualitatively, you expect that the signal grows as you go closer to the major, right? In time domain, the signal should do something like this. Okay, so, and the instantaneous frequency is ramping up. So how comes that the frequency, the amplitude in the Fourier transform goes down as you go closer to the major? Okay, this is also something that I record. This is because you see here the signal through is ramping up, but it's taking less and less time in each frequency beam. So this frequency beam received contribution from very few cycles. This frequency beam received contribution from many cycles. That means that here it takes a lot of time, and here it takes very little time. So delta T1 is much, much larger than delta T2. I'll give you the exact formula in a second. But I mean, here the signal takes a lot of time. Here the signal takes very little time. So despite the instantaneous amplitude being much larger here, when you take the Fourier transform, the signal goes down in frequency.
So you would see, even for one single source, you would see like this particle and not some oscillation.
So this is the amplitude. Sorry, this is just the amplitude of the Fourier transform. Of course, you see oscillations, but you know the amplitude of the oscillation. Okay, I move on. Okay, and then one important thing that you have to remember. So what happens is that the output of the gravitational wave detector is one scalar thing. So you see the intensity of the light is one scalar, and gravitational wave comes in two polarization, like any honest massless field. So the output will be a linear combination of the two polarization. That's really heuristic, and you cannot escape this. So we call F plus the coefficient of the plus polarization, and F cross the coefficient of the other polarization. This is really heuristic, very general. Why not quadratic, cubic? Again, H is so small that we forget everything which is not linear. At the detector, of course. There are a lot of non-linearities at the source, but at the detector, gravity is very, very, very linear. So at the end of the day, you get the output of the detector, which is a coefficient times one polarization plus another coefficient times another polarization. These are the actual value in this color code of the amplitude of this pattern function, as they're called, these coefficients. And as you can see, for instance, for the LIGO detector in Louisiana, you have maximum sensitivity if you are, if the signal is actually exactly from above. Let me give you, yeah, this plot is more meaningful. Is about the sum of the squares of these pattern functions. So as you can see, on the top of the detector, for the signal coming from the top of the detector, you have maximum sensitivity. From the signal coming from the bottom of the detector, equally maximum sensitivity. But then you have these four regions where you have zero sensitivity. They correspond to the four blind region because the interferometer here is the arms are 90 degrees. If a wave arises at 45 degrees, the interferometer is blind, no? Just because it will affect symmetrically the two arms. So since we are sensitive to differential motion of the two mirrors, so if the signal arrives at 45 degrees, you are blind. So for every detector of this type, you get four blind spots, no way out. Even if the arms are not at 90 degrees, are at 60 degrees, then you still have four directions to which you are blind, and you cannot escape. So these are the four directions which are blind for the LIGO Hanford. These are the four directions we are blind to for the LIGO Livingston. As you can see, the two detectors are very much aligned. So the four blind spots are very much in superposition. Of course, the Earth is rotating, but from the point of view of the detector, those four blind spots are always there. And then for Virgo, no, the four blind spots are in a completely different location in the sky. Because of, I mean, first, you know, the Earth is round, so it's very difficult to make two detectors align when there are a few thousand kilometers apart. And second, it's good to have something that is misaligned. So basically, if something comes from the blind region for two detectors, then it might not be in the blind region for the other. So you are starting patching up the full sky. But for the first two detectors you must have them aligned, because you don't want to have the uncertainty when you see something in one that if the other was well aligned or not. So the first two detectors, you want to have them aligned. So if one sees something, the other should see something with the same strength. Then when you start adding detector, then you might want to patch up those blind regions to cover them up too. But the first two detectors, you better have them aligned.
So the two LIGO detectors are aligned?
Are aligned, yeah, exactly. These are real pattern functions.
So
Yeah.
Brazil seems to be an ideal place to start.
I mean, if you go out of the plane, it's always good. So, you know, there was the plan to have another LIGO in Australia. Then the Australians pulled back in 2010. And then India came in. So India will have a LIGO detector. The land has already been bought. So in some years, there will be a LIGO detector in India. When after the detection in 2015, Australia tried to change their decision, but it was too late. So now it's going to be in India. But India is also.
The India is not too far from the antipode of Brazil. So if you do India and do Brazil, it's the same, more or less, axis.
Yeah, I mean, that,
Similar.
for third generation detector, there are.
Well, it means that if India is already much more advanced, so if you try to do one with not be covering something different, just what more or less India is already covering. It's a similar difference from LIGO and Hanford, right? It's
No, I mean, it always helps to have more detector because you need some redundancy. I mean, unless you get over 7, 8 detector, that might not help much. But until 5, 6, it always helps. The other question.
So this, if I understand correctly, this is the power mode you will mention. This would affect the amplitude you mentioned of the.
Yes, in particular on the blue point, the amplitude will be 0. So
So, but if you know this sufficiently well, you can correct for that and measure.
No, actually, this helps you to find the right localization. It's actually helping you. I mean, it's a feature, it's not a bug. It's a feature that helps you to localize. For instance, basically anticipating what I will show you later. With when you have detection by two, no? So
Well, but it's also a bug.
no,
It's also a bug in the sense that if you are in the blue,
Yeah.
it helps you that you know that you are, if you are, you should not be in the blue. But if you have a wave there, you're gonna be very poorly localized anyway. So you don't want to have a wave where the blues are. You want to have three in the red.
it's not that you don't have, you want.
Yeah.
I
But
mean,
no, you want to have as few blue spots as possible in the complete map.
in the complete, yeah, you want
That's
to
what
add, you want to add detectors.
localization.
The localization of where the is coming from.
Yes, it's very important.
And I thought this could, is affecting the amplitude of the way you're measuring.
Yeah, absolutely. It's affecting them. In particular, the amplitude here goes to zero, so you won't
Yeah.
detect anything from there.
All these patterns very well. You measure your amplitude, you correct. Your current.
No, exactly. I mean,
Measure the maximum amplitude, or not the maximum, but the correct amplitude, you correct for that.
yeah, I mean, what you measure is a combination of this factor and the intrinsic amplitude strength, polarization strength. And so, yes, you need to disentangle the two. And of course, with one detector, and the two LIGOs in this sense are one detector because they're sensitive to the same combination. With one detector, you simply cannot. You need additional information.
Your direction is the only old the electromagnetic counterpart, or can you?
No, for the gravitational wave detector are self-calibrating in the way I will describe in 5 minutes. That means that you do measure the distance. You do not measure redshift, but the distance, basically, the GR tells you what is the distance in a way that I will specify in a second. But let me just wrap up the discussion about the sky localization. No? So this is the map of the sky, and this is the basically the galaxy, say. And these are the 4 blind spots. Basically, a galaxy is a circle in the sky. So whenever you have one time delay between two detectors, by the way, I haven't told you, but I mean, gravitational wave detectors are very good in time delay. Basically, you have very good precision, unless you screw up the wafer, but you have very good precision. You have millisecond, tens of millisecond precision in the time localization of the arrival. In this sense, they are sort of orthogonal to optical observatories. Optical observatory, you need to observe the whole night to accumulate light, and then you have very good precision in the sky, but you don't know exactly the time. Here we have millisecond precision, tens of millisecond precision in time, but we have broad patches in the sky, like tens of degrees squared. So when you have a time delay selects a circle in the sky. In galactic coordinates, I mean, in celestial coordinate, a circle in the sky is a double banana, like this. But whenever you see a sky localization by LIGO, you never see one connected region, because this double banana will always intersect at some point the blind spot. So at the end of the day, I will show you later, you always get some single banana shaped, even for 2 detectors. For 3 detectors, you can really get a spot, no? Because when you have triangulation with 3 detectors, you really get a spot. But even in 2 detectors, you never really get always a full circle, because the full circle is bound to hit the blind region. So you always get less than a full circle of sky localization. Yes.
I guess, I don't know. I'm thinking that since the Earth is rotating, each of the detections that you have, you can have like this blind banana, let's say. But since you all, like, there's no Antarctica or like Arctic regions, I guess that you are have like full night sky coverage.
Yes, but I mean, if you average over the day, basically the modulation of the sensitivity is very mild. It's 10, 15%. If you take this and you average over the day, the modulation becomes 10%, 20%. So on average, these are kind of isotropic detectors, on average.
Just curiosity, how long does it take for each event? How long?
So it depends. Okay, this I will show in a slide later. Basically, it depends how close you are to the merger. So if you are very close to the merger, it can take a split second. If you are at the entrance of the bandwidth of the detector, it can take a minute. If you go to lower frequency, basically the duration scale as f to the -8, f to the -3, basically. This is analytic. I will show you later. So basically, going down in frequency allows you to gain f to the minus 3. So reducing by a factor of 3 the lower frequency of when the signal enters your detector has increased the signal duration by a factor of 27. Okay, so going down in frequency is allow you to accumulate a lot more data, which is good from the physics point of view. It's bad for data analysis because it makes data analysis more complicated, but we shouldn't be scared of it. Okay, so basically the order of magnitude of the duration of the signal changed very steeply with the initial frequency, they start in band. So for LIGO signal, it's usually split less than a second, just because we see them very close to the merger. They enter in band and they merge immediately, and so they're really short. But for third generation experiment that stretch this noise curve, or for LISA, basically you will see signal all the time. Basically, you turn it on and the signal will stay in band all the time. I will show you. For third generation detector, you can get even day-long signals. For LIGO, no. For LIGO, the longest signal you can get is minutes.
So just to come back to this question about the rotation theory, of course, we're sensitive to gravitational waves comes from below.
Yeah, yes. I mean, they're completely symmetric. Of course, the Earth has zero cross-section gravitationally.
About the polarization, mean change the polarization, change also the sensitivity.
Yes, I mean, slightly. Yeah, there is a minus because in this plot, I show the quadratic sum of the two polarization, but the two polarization, they have, you see, they have a slightly different pattern. No? This is the plus and this is the cross. So yes, the fact is, when the two detectors are co-aligned, you measure the same combination of the two polarizations. So you're not scientists. You need at least two non-co-aligned detector to measure the two polarizations separately. That's why Virgo is so important, because the two LIGO measure the same polarization, so you don't know which is which. If you add Virgo, then you're measuring the second polarization independently. But of course, Virgo will always have non-optimal sensitivity to LIGO detection, because LIGO detection are more likely to come from the high sensitivity region in that moment. And it's very unlikely that Virgo will also have high sensitivity in that moment. So when you see that Virgo is always lower than SNR, it's not the effect of the hardware. Yes, it's true. The hardware of Virgo has less sensitivity by a factor of 2. So for any event, Virgo will have lower SNR because of this, because the noise curve. But there is a prejudice, no? There is a, because you don't always have to blame Virgo, because all the signal you look in triple coincidence must first be in the two LIGO coincidence. And so they must come from a high sensitivity region of LIGO in that moment. And so you lose a factor of 2 because of the natural sensitivity of the experiment, and you lose a further factor because you might not be in the best sensitivity region in that moment for Virgo. So for sure, Virgo will have lower sensitivity on the signals that are detected and published. It's not only a problem of this, the Virgo being less sensitive. Okay, yes.
There are also blind spots for the triangular.
Yes, no, for triangular, do you have blind spot for triangular? I think completely blind spot, no, because whenever it's a blind spot for one pair, it shouldn't be blind spot for the other. But then you lose redundancy.
I think there's a blind spot also.
Or there is a blind spot. So,
Because you're only modulating one.
Plane out.
so I don't think there is a blind spot for the three, but the problem is that when you start losing one of the detector, you start losing redundancy, and so anyway you lose the advantage of having multiple detectors. And so since in the triangle case the multiple detectors are collocated, they suffer from correlated noise. Then if you start losing the redundancy, you have a problem. Okay.
I think I misspoke. You're right. I think there's no blind spot. There's just some black in the plane. You don't get the polarization.
Exactly.
Otherwise, you get something.
Yeah, because when you're coming from the plane, so you are blind for at least some of them, and so you lose information, redundant information, the polarization. And okay, now I'm getting too much into technical, but let me throw this element as well. So what happens is that at the end of the day, you have to compare to noise. And of course, at this level of sensitivity, we're looking at this relative displacement of 10 to the minus 20. You really need to compare to a lot of noise. So if you start losing redundancy, the noise level goes up. And so you have to reduce your threshold. Basically, so what do you have to do to claim that that something is a signal. You look at the SNR of your event, and sorry, this is the PDF, and this is SNR. So suppose you have some event and some given SNR, so you have to compare with the PDF, the probability distribution function of pure noise. How do you estimate pure noise? You just correlate signals, shifted time. So you take the LIGO output, you take another LIGO output shifted by 1 second. For sure, it's not a gravitational wave because the light path between the two is milliseconds. So when you have a coincidence between shifted time stream, then for sure it's noise. So you take this is usually linear in a semi-logarithmic scale. So if you plot the number of detection, the logarithm of the number of detection of spurious signal as SNR, you get this linear thing. And then you have to compare what is the SNR that you get for the actual event. So when you get an SNR of 10, you have to compare what is the rate of having something spurious at SNR 10. And then you say, okay, then we are that much off the PDF of the noise, so we can claim it's a signal. If you start losing redundancy between detector, then this PDF blows up, and so the significance of your detection at a given SNR will go down. I don't know if this was clear. Sorry, I didn't have a slide on that. But the idea is that when to claim a detection with some significance, you have to compare to the noise level. How do you assess the noise level? By making coincidence with shifted time. So the distribution of coincidence with shifted time, it just decreases exponentially with the signal to noise ratio. So if you go to high signal to noise ratio of coincidences, you know it's a real signal. But if for some reason the background of the noise is increased just because you're looking not a triple coincidence but a double coincidence, then the significance of your detection goes down. Okay, sorry, this was a bit technical. It was not in the slide, so I guess most of you didn't follow. But the idea is that it's important to assess the background. And so once you compare to the background, you can assess, I mean, that you have to compare to the background is something, you know, so vague in general that you can easily accept. The idea is that you assess what is the background by taking coincidence a shifted time. And of course, the more coincidence you are shifting, the more the background goes down. I mean, double coincidence, they have some distribution, triple coincidence, they have a lower distribution, and so on. So to assess the significance of detection, the more detector you have at play, the easier it is to have an assessment of the significance. So if this is the distribution of noise for a double coincidence, for sure the distribution of noise for a triple would be lower. So you can set your threshold for a given force runner. You can set your threshold to a lower SNR if you're talking a triple than double. Okay, so having more detectors allows you to set your threshold for SNR for claiming an event to lower level, so you can get more events. I mean, this is very broad and very general that I guess you can accept.
There are different pipelines even, right? That can assess.
There are different pipelines to assess the level of the background, and so as a consequence, the significance of the detection. So when you have more pipelines, it's good because you look for redundancy and you look for consistency, but you have to be careful in trial factors, because if you have a large enough number of pipelines, sooner or later you get some excess. Okay, so yes, it's good to have multiple pipelines. There are at least 3, but you have to look for consistency among pipelines, which is of course done.
Even outside the collaboration.
Okay, so there are different pipelines within the collaborations, and there is a pipeline outside the collaboration. Maybe some of you has been collaborating with the Princeton group. No, they have their own pipeline. So it's not completely independent because they use the same waveform as LIGO Virgo. But apart from the waveform, they use completely different noise estimation, completely different background estimation. And the results are usually consistent with LIGO. They actually get more events, not less. But all the events, so LIGO is conservative, as you should be. And then everybody can redo the analysis on the LIGO public data and reobtain the LIGO data and the LIGO events and more, which is fine. But for the moment, no inconsistency has been found. The only caveat is that they don't use independent waveforms, so that is not independent. Okay, so these are the actual pictures of the detector. This is in Hanford, Washington. This is in Livingston, Louisiana, and this is near Pisa. The tower is over there. So there have been three science run, observation run that are over, and now we can call them observation run because they have actually observed. And then there was the fourth observation run. The first half of the fourth observation run is ended already. The second half is not really half in a matter of time, but let's say the second part of the fourth observation run has started, and will end. There's no fixed date, but in 6 months from now.
That should be 24, not 25 for the O4A.
Sorry, this is wrong. This is 24. Yeah, thank you. Of course, because it's ended already. Okay, so then there is GAGRA that is joined the collaboration right now. It's in the same site as the Kamiokande experiment. So it's a place where there's a lot of science going on, but let's keep, okay, this is the catalog. So there are, okay, I think I will, most of my slide will go to the discussion section, but I mean, that's fine. Okay, there are a few important things, I mean, that I cannot bypass here. Okay, this is the events that have been collected so far with the 3 observation runs that have been fully published. So the 4th observation run has not been fully published in the sense that the parameter estimation of the over 100 events of the 4th observation run has not been published, but you can go to this GraceDB website, as been mentioned also last week. You can get preliminary information about the preliminary triggers, which has not been confirmed yet. But let's stick to the 3 observation run whose observation has been confirmed and published, and all the data are available and everybody can look at. So you see there are okay, first of all, we need to see compact objects, not compact object because of the frequency. So Earth going around the sun might give rise to gravitational wave, but surely not at the right frequency. So to have frequency of 10 Hz, 100 Hz, you need 100 rounds per second, and 100 rounds per second you can only have if the source is so compact that it doesn't smash into each other. Okay, so you need compact object. The only compact object we know about are neutron stars and black holes. And even black holes, they cannot be too massive because then they start not to be so compact, and so they start to exceed hundreds of kilometers, and so they fall off this bed. So these are neutron star will match here. 5 to 5 solar massive black hole will match here. 60 plus 60 solar massive black hole will match here. 100 to 100 solar massive black hole will match outside, and we don't see them.
For example, if you have an MRI.
No, an MRI means that extreme mass ratio in spiral, it means that there is a difference in masses by a factor of a ratio in masses by a factor of 10. By definition, they cannot enter LIGO because to have mass ratio a factor of 100, sorry, to have a mass ratio of factor of 100, you need one of the two to be more massive than 100 because the other cannot be less massive than 1 solar mass because then it wouldn't be compact unless there are primordial black holes, but okay. Let's say there is no compact object below 1 solar mass because there's no way to form them astrophysically. And so MRIs, extreme mass ratio in spiral, so objects with mass ratio above 100 cannot enter LIGO just because the total mass must exceed 100, and so the merger would be too low frequency. And so you see the most of the detection are concentrated to a few tens of solar masses because, of course, having more mass allows you to see things farther away, so it's good to have 20, 30 solar masses. We don't rule out few solar masses, 5, 6 solar masses, they're also there, they're just, we don't see them far enough, so we cannot see many of them. And we see a handful, actually, just a couple of binary neutron stars. These are the binary neutron stars that merge to form probably a black hole. And this is nice because this is basically the first ever black hole ever detected in the mass gap. So there are 2 mass gaps in the literature. It's important not to make confusion between the 2. So as you can see, there is a mass gap here, I mean, even visually, okay? So the scale has been adjusted so to make the mass gap very visible. So when you form in this traditional formation mechanism of compact object, you need a star, and the star has to go supernova and has to collapse. So if the star is not too massive, it won't give rise to a compact object. I mean, it won't give rise to a black hole, but it will give rise to a neutron star. If it's more than 20 solar masses, then we'll have enough gravitational pull to form a black hole. The current understanding of implosion of a star tells that either if it's not too massive, so it forms a neutron star, or it has to be very massive and form a black hole of higher than 5 solar masses. This is not a bound based on fundamental physics. It's a bound based on the collapse mechanism of a supernova. Okay, so the collapse mechanism of the supernova seems to predict that you have a gap in this region. And this was confirmed by the first 3 runs, but there is an event which is not here because belongs to the 4th observation round that falls right in this gap. Of course, there's nothing wrong with the astrophysical mechanism, nothing intentional with the astrophysical mechanism to have the result of a merger to form the mass gap, because this black hole is not formed by the astrophysical collapse of a star. No, this is formed by the fusion of 2 compact objects. So this is nothing intentional. But there is one event which is not there because belongs to O4, which is this event that you see. It involves a 2.5 solar masses object, which is still okay with neutron star, kind of tension, but it's okay. But a 4.5 object cannot be neutron star, and it cannot be a black hole formed the collapse of a star through the standard mechanism of collapse of stars. So either we don't understand something of the collapse of star, or this object didn't come from the collapse of a star. So this is about the low mass gap. There should be a low mass gap between 2.5-ish and 5 solar masses that seems to be violated, but it's only one event, of course, you need. And then there should be a higher mass gap, around 60-70 solar masses. This is due to the fact that a 60-70 solar masses black hole could come from a star of over 200 solar masses, and those are known to be unstable because at the core, the pressure is so high that you can form electron-positron pair, and they should blow up the star. So basically, there should be no progenitor, according to the standard astrophysical mechanism of formation of a black hole, that would give rise to black holes of 60-70 solar masses, but we do see a couple. So there is also a little bit of a problem with this higher gap. But
Sorry.
yes.
The total mass of the.
No, this is for each detection is 3 black holes. You see, 1 black hole, 2nd black hole, and merger.
So this would be the. No.
Yeah, you might not see this, but I mean.
The 2 and the final.
Yes.
Option.
For each event, you have 3 measure of masses. Yeah, you can Google it.
That one of you, I'm an astronomer. How?
I do. I'm
Yes.
gravitational wave astronomer.
Yes, I know what rather. So from people from Stella, the people that do star evolution, how large, how massive a star can be, because I know the rationally how in the universe, how massive the star can be. Because I heard of tens or hundreds of massive stars.
Sure. Why now? Because they wouldn't be alive today, you know? Very massive stars, they should have a little, and you are a astronomer, you know what I mean? So
they don't form to you are talking about the first generation of stars. It will be
for instance, we don't know yet, but that's the option that, you know, first generation of star or maybe 2nd generation of star should have, or even POP3 stars, it should be more massive because they would have less metals, no? So this is just a generic thing for newcomers to the glazing world of astronomy like me. You have in the primordial universe, you have less metal for astronomers. Whatever is beyond hydrogen and helium is a metal. And so a star made of low mass elements will have fewer absorption lines. Fewer absorption lines means that the stellar wind are very inefficient for a diet of the star. So the star can grow massive and fat. And so when in the primordial universe, you are expected to have fatter stars, more massive stars with less mass. Two things are related. And this should also have trigger a faster evolution of the star. So the star should evolve very rapidly and shouldn't be survived today. So the two things are related. This massive stars. They come from metal poor gas and shouldn't be survived today and shouldn't give reason to this population of black holes.
This experiment you saying that on the one hand, to produce a merger, they have to be binary or obtain a charge capture another companion at some point to actually merge. And the other thing is that the merger will occur a very high redshift, and you are observing an event which is.
Okay, so there are many things that here. Okay, we are jumping ahead, but since the question came up, let's do it now. So binary stars are very common. Half of the stars in the universe are binary, or more, even triples. Okay, so binary stars is very, very common. We shouldn't be misguided by our sign. Second, it's not too unlikely that the binary still is a binary after the supernova explosion. So once star goes supernova and become compact, the other star goes supernova and becomes compact. Of course, this might involve a kick, but surely not all of them are disrupted by the system. So even if 1% of the system survive in a binary after the double explosion, that's enough for having a binary of compact object. Then after the compact object is formed, you have a lot of time for the gravity to trigger the merger. And actually, the problem is the opposite, is that usually people think that the gravitational back reaction, because of the emission of gravitational wave, to trigger the merger is usually too long, it's not too short. Okay, so it doesn't matter how quickly the star evolves to compact object. The problem is to make the merger by gravitational emission within a Hubble time. That's usually the problem, because as everybody knows, gravity is very weak, so it's very inefficient in making the object merge. So the problem is the other way, to enhance the merger to see at the level of we see now, rather than the other way. Yes. Yes, I have a slide about that. Ask me again in 5 minutes or in the discussion session if I don't make it. Okay, and just to close up the picture about black holes, you know, black holes are usually, this is just jargon, but it's useful for you to know. Solar massive black holes is up to 100 solar masses that are the ones that fall in the LIGO band. Then you have intermediate massive solar black holes between a few hundred and 10 to the 4, 10 to the 5-ish, which nobody has seen so far. With some caveat, but let's say nobody's seen so far. And then you have supermassive black holes, which are 10 to the 6 up to 10 to the 9, which are the supermassive black holes at the center of galaxies like ours. No? In our Milky Way, we have 10 to the 6-ish solar masses. Those are the supermassive black holes that are either alone or maybe in a binary at the center of the galaxy. It's a huge question mark. What happens to the intermediate massive black holes? Is it just an observational fact that we don't see them? Or maybe there is a gap in the mass function of the black holes? I mean, you will tell me in 10 years. But this is kind of jargon, you know, solar massive black holes, intermediate and supermassive. LIGO looks at solar masses just because this frequency band. Future experiment with this terrestrial experiment can stretch a little bit the solar masses to scrape the surface of intermediate, but not too much. When you go to the to space experiment, where you can really look at 10 to the minus 3 Earths instead of 10 Earths, then yes, you have full access to intermediate and supermassive. Okay, so this is a slide that I prepared to illustrate what I told you about the sky localization. So you see, usually you should have a full circle in the sky when you have the time delay between two detectors, but usually this circle in the sky is broken by hitting the blind spot of the two detectors. But then when you have a 3 detector coincidence, then you really have a nice spot. So up to now, I guess there are order of 10 detection by LIGO and Virgo with the area in the sky of less than 30 degrees. Of course, if you are an optical astronomer, 30 degrees is basically the full sky. 30 degrees square, sorry, 30 degrees square. 30 degrees square, of course, is less than the full sky, but there are a huge amount of galaxies in there. I mean, that's the way it is. But and to have those 30 degrees square, out of the 100 detection, only 10-ish of them are really localized to this tiny region. Tiny. I mean, 30 degrees square is tiny for gravitational wave. It's not tiny for optical, of course.
Sorry, what's the distance between that?
Yeah, the typical distance is 100 megaparsec. So back on the envelope, you can say about this is basically the amplitude of the wave is mass divided by distance. So and you have to reach Mass divided by distance has to be 10 to the minus 20. Of course, mass and length are the same thing in gravity because of G. And if you put in the number of a solar mass is 10 to the 33 grams, but it's 1.5 kilometers. Divided by the 100 megaparsec, then you get the 10 to the minus 20. Basically. So 100 megaparsec is the typical ballpark. And luckily, you're looking at 100 megaparsec. Okay, let's skip it because otherwise you wouldn't see any. That's answering the question about the rates. So, one historical remark. So the blue band are the prediction of binary neutron star, mixed system neutron star black hole, and binary black hole made in this paper of 2010. So 2010, I was already part of LIGO Virgo, and we had this. I mean, not me, but astronomers, real astronomers, they published this band for the rate, the expected rate of binary mergers. This was based on what? This was for binary neutron star. You see, they were really good prediction, despite the fact, okay, of course, they embraced reorder of magnitude. Where did it came all the uncertainty? Because binary neutron star, we see 10-ish in our galaxy. Okay, in our galaxy we have binary neutron star. They are just millions of years away from merger, but we see them. So we are sure they were there. I mean, they must be there because we see them. And if you just extrapolate those, you can see because they are pointing their pulsing against us, then you can guess how many of them will merge per year in a megaparsec cube. And they should be order of, say, 10 to the minus 6-ish. That means 1 per million year per galaxy. So in a 1 megaparsec, so in 100 megaparsec cube, so in few megaparsec distance, you have one galaxy. And so the expectation of merger per galaxy is 1 per mega year. So you must look at least a 100 megaparsec distance to be able to see 1 per year. The year is the typical observation time of LIGO. So you have 10 to the 2 megaparsec compared to 1 megaparsec, which is the sort of typical interdistance between galaxy. So it goes with the volume. So 10 to the 2 to the cube gives you 10 to the 6. So this is the back of the envelope idea. Why you need to look at 100 megaparsec? Because at 1 megaparsec, you can expect a rate of 1 per year. If you integrate overall the galaxy within a radius of 100 megaparsec. And that's exactly what we saw. We saw 2 binary neutron stars at the distance of roughly 100 megaparsec. And so this ballpark of the astrophysical prediction was exactly confirmed. This is the red line of the observational band that we have now. And this dashed line was the median prediction from astrophysicists 15 years ago, 14 years ago. So you see, it was not too wrong, of course. It spanned 3 order of magnitude, but they were there. So, chapeau. I mean, congratulations to them. So for binary neutron star, for mixed system, they were even spot on. For binary black hole, they were not so right. So it means that what we see now is a bit on the optimistic side of the astrophysical prediction, but a bit, not too far off. Okay, so I heard many times in talks and say, oh, we see many more black holes than we're expected to be. That's not true, simply not true. I mean, you can download the paper and read it. Okay, we are a bit better than the average of the astrophysical prediction, just a bit. So is there the need? I mean, and this astrophysical prediction didn't require any fancy source of binary systems like primordial records, like some boost of encounter of three-body to full binary system. They just relied on the binary system we see in stars. Then we see basically most of the stars are in the three binary system, and just let them evolve, maybe with some gas triggering after the explosion. They might go through some common level, one star going very fast, so this giving some friction to trigger the approaching of the two. But you don't really need too much fancy physics to get this rate of black hole. Some exotic physics is allowed, but it's not required.
Thank you from observation in our galaxies and extrapolation. But for example, what we talked before about what happened in the early universe, not early universe, but when the first stars appear. I don't know if this is computed because in that case, you may have produced more line black holes that now you see the mergers.
That's exactly my understanding. As you can guess, I'm not an expert of this part of astrophysics, but yes, they were somehow underestimating the contribution from this massive star. I mean, this doesn't include contribution from POP3 stars. And POP3 stars are not there, it's just POP1 and POP2.
Riccardo,
there is a sense in which the BBH predictions and observations, actually not the predictions, but the observations are a lower limit, because for neutron stars, the frequencies are within the bandwidth of the detectors, whereas for binary black holes, you might have much more mass.
Oh, sure, but this is accounted for.
What? That
No, but the observational bias is accounted for by this prediction. This is the prediction of binary black hole in the LIGO band.
right in the LIGO.
Yes, this is the prediction of merging in the LIGO band. It was somehow inferred by the stars you see around, how many binary system, how long it will take to merge, and I mean, there are a lot of physics that fold in. That's why you get 4 order of magnitude uncertainty.
Just a quick comment for the GWTC3, the average distance that you find is above 1 gigaparsec, not 100 megaparsec.
Sure, no.
Yeah, just to
100 megaparsec is for
Yeah.
binary neutron star. Basically, the horizon for LIGO for binary neutron star is 150. And as a rule of thumb, you have to rescale linearly with the total mass. So if the horizon reach for binary neutron star is 150, then you rescale linearly with the total mass. Total mass of binary neutron star is 3, 1.5, 1.5. Then if you scale linearly, then you get to the horizon for BBH. That's why you get to the gigaparsec. It was correctly pointed out for a binary black hole of a total of 100 solar masses. Gonzalo, you had a question or was superseded?
I was going to ask if astronomers will make the same prediction today as they did.
Well, I mean, now there is a huge literature about what are these formation mechanisms. And the problem is that, I mean, I definitely not an expert on this, but I went to a conference where experts in this field talked. And what I got from that conference was that there are too many handles so far. Basically, the data are not constraining enough. There are so many handles to turn that it's better to wait for more data. Yeah.
The lore that I've heard is that every information channel with BBH mechanisms gives you 5 to 10% of the observed rate, and if you add them all together, you get about 150% of the observed rate. So clearly, like, we need better data. The constraining channel.
So basically 100 detection are way not enough to constrain the formation mechanism. There are a lot of room. So Chair, I'm
The discussion is.
yeah, it's already happening. So that's my idea, but let's see if the chair and the audience agree. So I wanted to open the floor for the discussion gravitation wave, then let Raul talk more violently about cosmological applications.
So, yeah, so the sketches that we have.
Or you can finish and I talk in the afternoon, like with plan also. I mean,
Yeah.
Up to the chairs, which.
No.
Especially afternoon.
So we can,
I mean, I can go on for
I mean, not even half your slides. so
yes.
that's
No, but
not
this was supposed to cover also the discussion session. So overall, I'm fine. Overall,
following, that's my proposal. We break for 15 minutes, we come back and Ricardo continues. And then,
yeah,
I think the idea was they kind of wanted to have.
Yes,
a
but-
before, so the discussion was more broad.
but then, yeah, but Ricardo can finish his talk and then
But
Raul.
he's saying that the more or less the rest of the slides are for the discussion. Is that-
okay. I would say that I should go to slide. Okay, here are the discussion. I mean, I have 10 more slides before the real, more controversial topic starts. So all what I'm saying now, as you can guess, is really background level.
But what is wrong in having a break and then?
Yes, no, break is always.
Then Raul goes in the afternoon as planned.
I will just comply.
Because after the break is discussion anyways, right?
Yes,
That
yes.
was the original schedule.
Okay, so
Yeah, they don't know. Those-
I mean, if I choose, then let's have coffee, and then I come back to setting the rest of the floor, and then there is Raul talking about real cosmological applications, and then we have a further discussion in the second part of the afternoon about.
That's fine with me. Is that okay? Okay, so let's break, because otherwise it's too long. Great. Right, for like, that's all.
Consegue.
So we come back.
Tinha bastante fazer uma ótima gripagem. Diego, eu gostaria de tirar aqui.
It's good.
Professoral, assim.
Não, isso é ótimo. Mas mantém o original.
Não, que é a palestra de uma hora, mas são uma palestra das fixa, uma hora e meia.
Não, mas ninguém
Por intanto che as pessoas tirano.